This conference will now be recorded.
So, very good evening, students. Today we'll be completing this chapter atoms by learning these topics I have written here. De-Broglie's explanation of Bohr's second postulate, that is quantization, and we'll see that there are some limitations of Bohr's theory as well. Then that was again further developed by other scientists. So those you will be learning in your higher studies in the atomic structure modern physics part. So we'll see only the limitations. That means which facts of the atoms or related to atoms could not be explained by Bohr's theory. And today the most important part is the numerical examples. We'll take few of them. Like we'll see how in various competitive exam numerical problems are being asked from this particular chapter. So let us learn first this topic, de-Broglie's explanation of Bohr's second postulate. So what is the Bohr's second postulate? Do you remember? Bohr's second postulate. Yeah, good evening Deepa. You have also arrived. So I are just about to start today's class. So de-Broglie's explanation of Bohr's postulates, that is quantization postulates, we'll learn second postulate, and limitations of Bohr's theory and numerical examples we'll be discussing today. So let us start. See, Bohr had given a very important, and also uh, useful postulate. The second postulate, that is the quantization of the orbits. Quantization of the orbit. What does that say? That electrons will be revolving around the nucleus not in any arbitrary orbits. Only those orbits are allowed for electrons to revolve around the nucleus for which the angular momentum will be integral multiple of nh by 2 pi. H by 2 pi is sometimes written as h cross. So this angular momentum of any particular orbit, if that becomes equal to integral multiple, this is the integer n, integer number. So integral multiple of h cross, then that particular orbit is a stable orbit, that is called stationary state. So we'll see how this actually is derived. This particular postulate can be derived from de-Broglie's hypothesis of matter wave. De-Broglie's hypothesis of matter wave. So what is de-Broglie's hypothesis? De-Broglie's hypothesis states that any particle, material particle which is in motion, it is also associated with the wave character. So material particle in motion is associated with wave character. and that wave character can be expressed in terms of lambda is equal to h by p, h by p or h by mv, where p or mv is called the linear momentum. Okay, so this is the Bohr's hypothesis. Okay, now let us see how Bohr's hypothesis can accurately tell you or can help you to derive Bohr's second quantization or Bohr's postulates. Bohr's postulate, that is yeah, the second postulate, that is L is equal to NH cross. So this postulate. Okay. All right. Now let us see. Let us take just simple thing that let us suppose an electron is moving in a circular orbit of radius r, as you see from this figure. So electron is orbiting around the nucleus in a circular orbit of radius small r. Okay. So in this case, this particular orbit will be stationary orbit. This particular orbit will be stationary orbit only if L or mvr, suppose the speed of the electron in this particular orbit is v. So mvr is the angular momentum in this particular orbit. If this becomes integral multiple of h cross. Okay. Now look in this. So this is the Bohr's quantization for this particular orbit. Now let us see. According to de-Broglie's hypothesis, this particular electron, which is revolving around the nucleus in this circular orbit, also associated with wave character. Okay, with wave character. So hence circular orbit can be taken as a stationary state. Hence this circular orbit can be taken as a stationary state only if. So let us see. So what we can say, that according to de-Broglie's according to de-Broglie's we'll write that's it. So according to de-Broglie, electron in this orbit will be associated with wave character. Okay. All right. So you look in this case, if you see this, if the wave is like electron is having having a wave character, it will actually create a stationary wave. Okay, stationary wave in this particular orbit. Okay, and at the resonance condition, at the resonance condition, if you remember from the production of stationary wave from the 11th standard class, see, if suppose there is a string of length L. Okay, so this L has to be at the resonance condition. This stationary wave will be produced, and at the resonance condition in this particular string, the length will be is equal to integral multiple of lambda. So in this case, if we apply this particular condition for stationary waves to be produced in this particular orbit, so this particular orbit will be stated or considered as a stationary orbit. This orbit orbit can be can be taken as a stationary orbit if only if 2 pi r is equal to n lambda. So this actually this length will have integral multiple number of wavelength. Okay, so then only this particular orbit will be a stationary state. So if that is the case, look, this is the condition we have got for this. Let us rub this portion, clean this portion. So this is the condition for this particular orbit to be a stationary state. Now, okay, let me clean everything. I'll write this condition 2 pi r is equal to n lambda. This is the thing we know. Now look, this lambda by de Broglie's hypothesis we know lambda is equal to S by P or S by mv. Okay, if we put it here, look, we'll get 2 pi r is equal to n h by mv. Okay, now mvr in the left hand side, this is n, this is h by 2 pi. So this is nothing but nh cross. Okay, and see, this is nothing but the angular momentum is becoming nh cross. Look, this is the postulate which Bohr had made for stationary orbit. Okay, this is called quantization condition, and this is the number which is called principal quantum number. Principal quantum number. Principal quantum number. Qn. Okay, so you can see that this famous Bohr's quantization condition for angular momentum can be obtained from the de Broglie's hypothesis of matter wave. That's how this postulate is actually proved to be very, very true. Okay, very, very true. So this is called de Broglie's explanation of Bohr's second postulate, that is quantization condition or quantization. Okay, I hope you have understood. I'll just repeat it quickly, that if we just consider an electron revolving around a nucleus in the orbit small r, this particular orbit can be called a stationary orbit when there will be a resonance condition, and that resonance condition can be stated actually in comparison with the stationary waves at resonance condition in the string. If you remember, in the 11th standards knowledge it is, okay, if you remember that, so this condition is satisfied if this length is L, this L is equal to integral multiple of lambda. If this is satisfied, then the orbit will be a stationary orbit. So that is 2 pi r is equal to n lambda. Now by de Broglie's hypothesis we know lambda is equal to h by p. Okay, so lambda is equal to h by p. P is what? P is m into v. M is the mass of the electron. V is the speed of the electron in that particular orbit. Okay, and if we put this value lambda over here, we plug this value here, then what we get? 2 pi r is equal to n h by mv. So now look, this mv and r in the left hand side, 2 pi goes down. Okay, just beneath the h by 2 pi. So this is h by 2 pi, and in the left hand side you look mvr, and this is the integer number. So this is mvr is equal to nh cross or nh by 2 pi. So this is the postulate. So we have arrived from two things, like two wave characters or stationary, a condition for stationary wave, and de Broglie's hypothesis. So these two things we have used here. Okay, all right. So sometimes there will be a question. Sometimes there will be a question. Uh, you will be asked to find out the angular momentum for third orbit, third stationary orbit. How do you find out then? Angular momentum for third stationary orbit. How do you find out? So you have to simply write nh cross. So n is equal to 3 over here. So 3h cross. So this is the answer. Angular momentum in the third Bohr orbit. Okay. All right. So now we'll see there are few limitations in the Bohr's theory. We'll just discuss those things, but not very great detail. You have to keep this in mind as an information. So this theory, Bohr's theory, is applicable only for the hydrogen or hydrogen-like atoms. What is hydrogen? You look, hydrogen atom has only one proton, one electron. Most importantly, you have to remember that hydrogen atom has only one electron. So this is called simplest element. Okay, simplest element. So it has only one electron in the outer orbit. One electron in the outer orbit. So this is hydrogen atom. Okay. What about hydrogen-like atom? Hydrogen-like atom may have any number of protons inside. Okay, but it has to have only one electron in the outer orbit. So those atoms which has atoms or ions, those ions which have which have only one electron in the outer orbit is called hydrogen-like atoms. See, like if I take helium atom, so it has two He4. That means it has two electrons in the outer orbit. Okay, two electrons in the outer orbit. But if you just take one electron off, okay, one electron off, then it becomes singly ionized. Singly ionized, that is He plus. So this is called singly ionized helium atom. Sorry, helium ion. And this helium ion, singly ionized helium ion, is just like hydrogen atom. Okay. Similarly, lithium has three over here, three. Okay, so three electrons should be there. Okay, three electrons should be there. But if I take doubly ionized lithium, then in the outer orbit there will be only one electron. That is also just like hydrogen atom. So these are called hydrogen-like atoms. So this Bohr's theory is applicable only for hydrogen or hydrogen-like atoms. So it cannot explain when there are like with the atoms which has more than one electron in the outer orbit. Okay, it cannot explain the things like spectrum. It cannot explain the spectrum of those atoms with electron more than one. Now in the hydrogen spectra we see certain, actually there are no single lines. Okay, not only single line. What we see, some lines are in a group. That is called, these are called spectral series. Actually, why do we get this spectral series? Exactly, we don't know from this Bohr's theory. Okay, we don't know exactly why we get this kind of series. Then, but it can give you the frequencies and formulas for various frequencies in the spectral series. But we don't know why this arise actually. Exactly, why does this arise? And see, it cannot explain some lines you see in the spectrum. Some lines will be very bright and some light will be very faint. Okay, so why this intensity distribution is happening? Why not same intensity for all the lines? Okay, that means probability of various transition it cannot explain. Probability of various transition it cannot explain. Okay, so it does not explain. Okay, this will be why only circular orbit can be taken. Why not elliptic orbit? So this is, see, in case of planetary motion we have seen there are elliptic orbits, and this Bohr's atomic model or Rutherford's atomic model is more likely to be equivalent to the planetary system, the structure of the planetary system. But in the planetary system, Kepler's law said that electron, all the planets are revolving around the sun in elliptic orbits. So elliptic orbits for atomic like electrons to be revolving around the nucleus is also possible. Okay, but why Bohr had to take only circular orbit? So that is also not known. Actually, elliptic orbit is the correct thing. So this will be actually Sommerfeld and other scientists. They will be explaining this thing why you should take elliptic orbit, and elliptic orbit in special case will become, see, special case. This is elliptic orbit. So here there are major axis and minor axis A and B. So when A become B, that will be circle, isn't it? So elliptic orbit can be more precise to explain the structure or the orbits to be. And further again we will see in the quantum mechanics there is no condition, like no actual notion of orbit only. Okay, there will be, you will see in further like higher classes you will learn further that electron is a cloud and there is no definite position at particular time. It can, it can be somewhere, it may not be there also. Okay, so that is actually called uncertainty principle. If you go for quantum mechanics in higher classes again, you'll see uncertainty principle, and that's why we cannot say an electron to be confined in a particular orbit. So this orbit concept also is not very feasible concept. Okay, so that we'll learn in the higher classes. Okay, so this I have already told. The relative intensity of various spectral series or spectral lines could not be explained. That means probability. Why some transitions are more probable, more frequently happening, and some are not that frequent. Okay, it does not explain further splitting. See, I have some lines, and if I apply magnetic field, okay, if I apply magnetic field, okay, so we can see further splitting of this line. Okay, so there will be some very fine lines like about this main line, maybe more both sides. Okay, these are called fine structure or Zeeman splitting. And when you apply electric field, then also we'll see further splitting of the spectral lines. So further splitting of the spectral lines in presence of magnetic field is called Zeeman effect, and further splitting of the spectral lines in presence of Stark effect is called electric field is called Stark effect. So these two effects could not be explained by the Bohr's theory. So these were the limitations in the Bohr's theory. But for your curriculum, up to this only we'll be learning. and Sommerfield's model, and it's further you will learn when you go for higher studies with physics. You will learn about the quantum theory of atomic structure, etc. Okay, so now we'll see. We'll take up various numerical example depending on this chapter. Okay, depending on the concept whatever we have learned here, we'll try to solve these problems. So there is a first problem. Determine the speed of electron. Determine the speed of electron in third Bohr orbit. Determine the speed of electron in the third Bohr orbit. So to solve this problem, first of all, you should remember the formula for the velocity of any Bohr orbit. So that can be written as V is equal to speed. So see, nth orbit we have to find out. So you have to remember a formula, that is speed of electron in any Bohr orbit. A general formula, any Bohr's orbit. Okay, so I will not write Bohr orbit. In any orbit of hydrogen atom. In any orbit of H atom. So how do you write that? V is equal to C. There is, I'll write the original formula first. 2 pi k z square by nh. Actually, this is H and this is N. This is principal quantum number. If you put, so this is helium atom. Z will be 2 and N will be 3 here. Then so this K is actually 1 by 4 pi epsilon naught. Okay. So you have to put this value of this K. Z is 2, N is equal to 3. Okay, then you will get the value, and is the electronic charge. See, if you do this way, then you have to do a very rigorous calculation in the competitive exam. It is not very feasible. So better you remember a simple formula. See, if this, this can be actually converted to let me first write it. So let me write 2 pi k e square. 2 pi k e square, okay, by C into H. And look here, I'll write C by N. Okay, C I have multiplied. So this particular factor, this particular factor, if I just take Z is equal to 1, you keep Z over here. This particular factor is called alpha, that is the fine structure constant. Fine structure constant. And it has a constant value. This has a constant value. We can remember that value, okay? So this alpha has a value 1 over 137. 1 over 137. Now look, if we just use this alpha value, it is very easy to remember the formula. Look, so in terms of fine structure constant, we can write this part as V is equal to alpha by N into C into Z. Okay, just remove this part. Okay, now Z is how much? Z is 2. C is what? The speed of the light. Alpha value you know. Look here, I'll just put it. Alpha value I have here. This is a constant term. So 1 over 137. Then C means 3 into 10 to the power 3 into 10 to the power 8 meter per second. Speed of light in the vacuum. And Z is 2, right? And C, N is 3. So if you just do the whole calculation, if you do the whole calculation, see, you'll get a value. You'll get a value something like 1.45 into 10 to the power, or maybe it is 1.46 into 10 to the power 6 meter per second. Okay, this is the speed of the electron. So the main point what you have to remember here is, for competitive exam, alpha over n c into z. This is the formula. This is for any atom. If this is hydrogen atom, if you are asked for hydrogen atom, put z is equal to 1. If you are asked for lithium doubly ionized atom, like doubly ionized, yeah, atom, then write z is equal to 3. Then you get for all of them, like whatever you are being asked, you can calculate the speed for any orbit, like for an electron orbiting any orbit, n is equal to 2, 1, 3, whatever, and this z has to be put carefully. You have to take the value carefully. If it is lithium doubly ionized, then you have to take 3. Beryllium triply ionized, you have to take how much? 4. So these are the things you have to take. Okay, and this is the formula, you just remember. Alpha by n, alpha has a value 1 by 137. This is a constant term. Okay, constant value. All right, so we'll move on to the next question. So see, this question says, if the energy of nth orbit of a hydrogen atom is En. First of all, let us write what is the energy of hydrogen atom in the nth orbit. Minus 13.6 by n square electron volt. So this we know. If this is for hydrogen atom, H atom. Okay. For H like atom, hydrogen like atom, what you should write? What will be the modification in this energy? Hydrogen like atom. See, the modification will be En is equal to minus 13.6 by n square is all right. Along with that, it will be z square by n square. Okay, this is the modification you have to make for hydrogen like atom. So hydrogen like atom, see, if you put z is equal to 1, that will be hydrogen atom. See, this is the energy of nth orbit. Okay, nth orbit of hydrogen atom, like electron in hydrogen atom, and this one is the energy of an electron revolving in the nth orbit, but this is for hydrogen like atom where they have z more than 1. So in this case, look, if the energy of nth orbit of a hydrogen atom is En, so which we have written already, then the energy of nth orbit of a doubly ionized lithium is what? Doubly ionized lithium is what? Okay, look, doubly ionized lithium doubly ionized, actually it has 3. Okay, 3. Doubly ionized means it will be having it is actually hydrogen like atom, and you have to use this formula. So what is this formula? Let us say this is for hydrogen like atom. I'll write here for the time being as a prime, En prime, for hydrogen like atom. Here z is how much? Z is 3 for a doubly ionized lithium atom. So minus 13.6 by n square, it is as it is. So this also will be electron volt. And see what is changing over here. Z is z square, you have to write. Okay, z square means 9 square in this case. So look, this part is the energy of hydrogen atom, like, yeah. So energy of electron in the nth orbit. For hydrogen atom, this is 13 minus 13.6 as you see here. So this is 9 into En minus, okay, minus we don't have to write, 9 into En. Okay, this is the energy. So it is actually greater than hydrogen atom, 9 times greater than the electron in the hydrogen atom. Okay, so this is how here the answer will be C. Okay, now I'll go to the next question. Let me just read the question. So there is a question like minus 3.4 electron volt. If this much is the total energy of an electron in an orbit of an atom. Total energy means it is the sum of potential energy plus kinetic energy, that is called total energy. So total energy, suppose this is E. E is the total energy which is sum of potential energy and kinetic energy. Okay. So you have been given this total energy to be minus 3.4 electron volt. Then kinetic energy and potential energy you have to calculate. How much would be the kinetic energy and what will be the potential energy? So look, this total energy is being given. You have to calculate this too. How do you get it? In this case, you have to remember one trick, or this is the conceptual thing you have to remember here. That look, I'll write the expression for the potential energy for hydrogen atom, and that too for uh, let me write for the orbit, first orbit. For the first orbit itself, potential energy is actually given by minus k into z square by r. This is r. Okay. So this is the potential energy. What is the kinetic energy? Sorry, I'm just going to teach you one thing. You may not be remembering this thing, so don't have to. You don't have to remember. I'm just teaching you the trick what to remember here. This much things you may not be able to remember. So, but look, the kinetic energy is actually given as positive. With a positive, kinetic energy cannot be negative quantity, half mv square, otherwise v speed will be imaginary. So with a positive sign, k is equal to, see, sorry, this is k z square by 2 into r. You can look one thing and see, if you just add these two, what you get? You get minus k z square by 2r. This is the total energy you get. Look, these three expressions, I hope you are understanding me. These three expressions. This is this is expression for k is actually here 4 pi 1 by 4 pi epsilon naught. So this is the k, z square by r. This is the potential energy. If r is the orbit, like distance from the nucleus to that electron, or radius of particular orbit. Okay. So in that particular orbit, this is the potential energy with a minus sign. What does this mean? This means that it is under attractive or central force, uh, under the attraction, or under the influence of the central force. Potential energy negative means it is under the influence of or action of conservative force field. Okay. Now kinetic energy expression is kz square by 2r. You look these two expressions. So kinetic energy is nothing but, with a minus sign, potential energy by 2. Look, that means there is a relationship between potential energy and kinetic energy. If somewhere kinetic energy is being given, then you just multiply 2 with the kinetic energy and take the minus sign, you will get the potential energy. Okay. And see, then if I just add these two, kinetic energy and potential energy and kinetic energy, see, you will get this total energy. So this is nothing but equal to the kinetic energy. Here, look, this is the kinetic energy with the minus sign. Kinetic energy with minus sign. Okay. So if the total energy is given, see what will be the kinetic energy? Kinetic energy will be taken just minus of the total energy. See, minus of the total energy is kinetic energy. This is total energy. So so kinetic energy will be minus multiplied by the total energy. Look, out of these four equations, see four options, which one will be the true? See, then potential energy will be actually double of the kinetic energy, double of the kinetic energy with a negative sign. So look here, this is the total energy. So kinetic energy will be with a minus sign. Kinetic energy will be, kinetic energy is minus of total energy. That means plus 3.4. Okay. So actually B will be the option, correct option. And what is the potential energy? That is potential energy will be uh, 2 into kinetic energy with a minus sign, with a minus sign, with a minus sign. So it will be, kinetic energy is 3.4, so it will be minus 6.8 electron volt. Okay, this is the answer. Okay, we'll go to the next one. So see here, the question is, if the ground state energy of hydrogen atom is given, ground state means what? The lowest energy state, the lowest energy state, and that is happening in the first Bohr orbit. Okay, so we have seen that the total energy for hydrogen atom in any orbit is minus 13.6 by n square for hydrogen atom. And see, the lowest energy will be E1, that is when n is equal to 1, that is the first Bohr orbit. This is n is equal to 1, first Bohr orbit. Okay, this is the first Bohr orbit, minus 13.6 electron volt. Now the question is the energy of the first excited state of singly ionized helium atom. So you have to find out first excited state. First excited state, let us see. For hydrogen atom, what is the first excited state? For, or we can directly write for any H-like atom, H-like atom. What is the energy? We have seen minus 13.6 by n square into z square. Z is the atomic number. Okay, so here singly ionized hydrogen, sorry, helium atom. So Z will be 2. If we put it here, so it will be minus 13.6 into 4 divided by n square. So eventually you get, so this is 6 4 24. This is 52 into 2, so 54. So you get this much by n square. Now look, first excited statement what? N is equal to 2. So E2 will be the first excited state. Then this is n square. 2 is 4. So if you just do this division, you get the answer. It will be the first one, this one. Okay. This is the energy for first excited state, because ground state is n is equal to 1. First excited state means n is equal to 2. First excited state means n is equal to 2. And see, we are using here the energy expression for the hydrogen like atom. Okay, so this is the answer. Here A is the answer. Now I have got another two numerical problems, then I'll stop the class after solving that, those two. So what is the wave number of first line of Balmer series? Here, line of Balmer series, or number of the first, yeah, line of Balmer series in terms of Rydberg constant. Okay, in terms of Rydberg constant. So you have to find out what is the wave number of the first line Balmer series, first line of Balmer series. So we have to first write down what is the expression for the wave number for Balmer series. Okay, so what is the Balmer series wave number is written as 1 over lambda. So this is into the Rydberg constant 1 minus, see Balmer series means it will come to the second orbit, n is equal to 2. So final will be n f is equal to 2 and n I will be starting from 3, 4, 5, 6, etc. First means, see, okay, let me write for any transition, wave number will be written in by this expression in final square minus n initial square here. Okay, like that. Okay, so if the n f, that means where the transition is happening, and if it is coming from either 3, 4, 5, 6, anything, if they are coming in the second orbit or second, n is equal to 2, nf is equal to 2, so this is ni square. Okay, so if this is the 2, then it is called Balmer series. Okay, this is called Balmer series. This is the wave number, expression for wave number for any series, any transition, for any transition, this one, for any transition, any allowed transition, I should say, transition. Okay, but Balmer series is when the final state is 2, n is equal to 2. So that is Balmer series. Now let us see what is the first Balmer series when it comes from immediate next orbit. See, n is equal to 2, then n is equal to what? So this is nucleus, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, like that. So when n is equal to 2 is this one, the first, see, first one after this n is equal to 2, so that is n is equal to 3. When, so for first Balmer series or Balmer line, this ni will be just 3. Okay, so now you have to do this simple calculation, then you get the answer. So this will be 1 over lambda is equal to r into, so 1 by 4 minus 1 by 36, 1 by 9, and this will give you, this is 36, so this is 9, this is 4, so you get 5 by 36. So this is the wave number for first Bohr, for first Balmer line, and there will be obviously this part with an arrow r here, so 5 r by 36. So this is the answer, 5 r by 36. This is the first Balmer, like wave number of the first Balmer line, Now we'll go to the sixth one. Here, what is the ratio of minimum wavelength to the maximum wavelength of the Balmer series? So Balmer series, we know 1 over the wavelength. You have to find out first wave number, r is equal to 1 by lambda is equal to 2 square minus ni square. So this is the Balmer series. Where ni will be starting from 3, then 4, 5, etc. It can go up to infinity. Okay. Now See, for minimum wavelength, you know what you have to write for a minimum wavelength. For minimum wavelength. Okay, let me spell it. For minimum wavelength, n has to be equal to infinity. See, ni has to be infinity for minimum wavelength. Okay, for minimum wavelength, this is the thing. Now see, then we will get 1 by lambda minimum is equal to r by 4. Okay, this is the minimum wavelength. And then if we just take minimum wavelength, what is the wavelength? Then it is 4 by r. Okay, so we have got minimum wavelength. Now let us see what is the maximum wavelength. Then we have to take the ratio according to this question. Okay, so when it will be maximum, it will be maximum just immediately. Actually the wavelength will be maximum for the first Balmer line. Okay, so first Balmer line, this is max. This will be r into 1 by 4 minus 1 by first Balmer line is n is equal to 3. Ni is equal to 3. So this is 9. Okay. So this we have calculated that this will be 5r by 36. So lambda max will be, maximum lambda will be 36 by 5 r. Okay. Now let us take the ratio. What I'll do, I'll just remove this part. We know now what is the maximum wavelength or what is the minimum wavelength. Okay, so look here, the minimum wavelength is 4 by r. So you have to find out the ratio of minimum to maximum. Minimum to maximum, this will be 5r by 36. So r goes off, this is 9, so you get 5 by 9. So what you get is lambda minimum is to maximum for Balmer series is given by 5 is to 9. So 5 is to 9. Okay, this is the ratio. So this is how you have to solve various problems. So I'll stop it here and I'll leave you with various MCQ questions on this chapter. We have already, I think, uploaded. So you can just go and see in our site and you can practice this MCQs. And these are actually asked in various competitive exams. Okay. All right. So we'll stop it here for today. The next day we'll come up with a new chapter on Tuesday again. Okay. Bye for today. Not Tuesday, Wednesday.